Have you ever noticed that the airplane routes on a map appear to be curved? This is not just an illusion, of course. This is a mathematical concept called geodesic. And today I'm gonna teach you what they are and why they are really, really important. Let's go. So a geodesic is the shortest path between 2 points on a curved surface, like this one. While on a flat plane, the geodesic is simply a straight line between point A and point B. Things become more complex when the surface is curved, of course. On a sphere, such as the Earth, a geodesic is represented by an arc of a great circle. What's that? A great circle is any circle that divides a sphere into two equal halves, such as the equator, for example, or the meridians passing through the poles, like this. So I want to give you a practical example, a flight between New York and London. Let's consider this transatlantic flight. On a standard two-dimensional map, the shortest route seems to be a straight line directly across the Atlantic, like this. However, if pilots were to follow that straight line, they would actually be flying a longer route due to the Earth's curvature. Instead, airplanes follow a geodesic, so an arc that curves towards the north, often passing near Canada and Greenland, and this path is shorter in three-dimensional space, even though it looks curved when we project this path onto a flat map. So why does this happen? The Earth is spherical, and that means that the distances behave differently than they do on a flat plane, like this. A straight line on a map is rarely the shortest path in reality. Great circle rules, or geodesics, whatever you want to call it, take into account the curvature of the Earth, allowing airlines to save pressure, time, and fuel. So why this kind of mathematical trick is important? Well, we have two reasons. When we talk about navigation, so ships, airplanes, also satellites benefit from this kind of mathematical concept because they can optimize their trajectory and fly at the most efficient routes. We also have another reason, which is architecture and engineering. An example is the pipeline layouts over the bottom of the ocean. Let's imagine that we miscalculate, even for a little bit, the type of path that these pipelines have to follow. At the end, it's gonna cost us millions and millions of dollars because we didn't use a geodetic. That's gonna be crazy. So if you wanna find the best way to get from point A to point B in the most efficient way, now you know you have to use a geodetic. I'll see you on another video. Bye.